Hello everybody. I have already discussed about the ocean continent convergence. Now I will discuss about ocean convergence. Here it is mostly found in Pacific Ocean between the east oceanic part of the Eurasian plate and the Pacific plate. So most of the ocean convergence are seen in Pacific Ocean. That's why we have the circum-Pacific ring of fire. So the Pacific plate being heavy, it subducts below the Eurasian plate or with North American plate. Also Indo-Australian plate subducts below the Pacific plate or Eurasian plate. So what are the examples? Examples are Aleutian Trench, which extends between Alaska of North America and Kamchatka of USSR. This trench has been produced by the convergence of Pacific plate below North American plate. So Aleutian Trench. Then we have the Kurile Trench. It exists between Kamchatka to Japan. Here, Pacific plate subducts below the Eurasian plate. Towards the eastern side of Eurasian plate, we have the oceanic part of the Eurasian plate. So, with that, the Pacific plate interacts and Pacific plate goes below the Eurasian plate near the Okhotsk. Then we have the Japan Trench. It is the convergent zone where Pacific plate subducts below the Eurasian plate near Sea of Japan. Beside that, we have many other trenches. Ryukyu Trench, which is produced by Pacific plate subducting below the Eurasian plate near East China Sea or the Okinawa Trough. Then Philippines Trench. It lies east of Philippines. It runs north-south along the eastern margin of Philippines Island. Philippines Sea plate is subducting beneath the Philippines mobile belt. It is a part of the Eurasian plate boundary. Then we have the Mariana Trench, which lies east of Mariana Islands, further northeast near Guam in Western Pacific. Pacific plate is subducting below the Philippines Sea plate. Then Tonga Trench. It lies between Pacific and Indo-Australian plate. Here Pacific plates subducts. Similarly, we have Kermadec Trench. It is a Pacific plate subducts below the Indo-Australian plate. Similarly, we have New Hebrides Trench or Vanuatu Trench. Here, Indo-Australian plate subducts below the Pacific plate near North Fiji. North Fiji basin is the microplate. Then Burma Trench. Here Indian Oceanic plate subducts below the oceanic part of the Eurasian plate. That is Burma part, producing Andaman Nicobar Islands. So, these major trenches are all found to be located in Pacific Ocean and partly in Indian Ocean. The main features of associated with ocean convergence are trench, features in four-arc region, that is accretion and prism, four-arc basin, island arc, andesite line, back-arc basin, double island arcs, Benioff zone. So these features were also there in case of ocean-continent convergence. But here, this double island arc that we see, that is a main feature that is to be discussed, because others have been discussed in ocean-continent convergence. So the volcanism that takes place here because of melting of the subducted oceanic plate provides the lava of andesitic or rhyolitic composition which form the island arcs or polar arcs. The entire Pacific oceanic plate has subduction zones and trenches all around its north, east and western border, near which island arcs or islands of andesitic composition have been produced. The boundary of these arcs define the andesite line. What is the andesite line? It is the boundary of the volcanic arc towards the oceanic side, towards the center of the Pacific plate. And this andesite line corresponds to the circum-Pacific ring of fire, and thus it separates the basaltic rocks of deeper Pacific Ocean from the andesitic island arcs at the trenches, which originate near the trenches. The andesitic rhyolitic lava, being acidic, extrudes with explosion, producing a ring of fire. That's why we see that all along the border of the Pacific Ocean we find the ring of fire, which is called as circum-Pacific ring of fire. It is produced because the andesitic lava is found to extrude with explosion, because it is bit acidic compared to basic lavas. Basic lavas erupt quietly because they are highly fluid, so they cannot cause explosive volcanism. So we discussed about the trenches that are seen in Pacific Ocean because of ocean-ocean convergence, and the main feature which is produced by ocean-ocean convergence is the double island arc. So let us discuss. Double island arcs are not found in ocean-continent convergence, but are found in ocean-ocean convergence. So following are the mechanism of its formation and examples. Here two parallel island arcs are found to develop, being separated by the back arc basin or back arc trough. The first arc towards the trench is the front arc, which is convex towards the subducted plate. It is followed by formation of back arc basin behind the first arc due to tensional stress effective over the overriding plate due to mantle or asthenospheric convection current. It is followed by formation of second arc or rear arc through ocean floor magmatism or second chain of volcanoes. So, in case of double island arcs, the subducting plate, both are oceanic. Here, both are oceanic plate. The subducting plate produces magma, which comes up to the surface and produces a island arc, which is convex towards the subducting plate. So this arc is called forearc, and behind it occurs the back arc basin, and still behind the back arc basin that develops another arc due to ocean floor magmatism. So these two arcs, they form the double island arcs. Example. We have the Mariana Arc system. Mariana Islands form front arc and West Mariana Ridge form the rear arc or the back arc, both separated by the Mariana Trough. So Mariana Trough forms the back arc basin. Mariana Ridge, back ridge. And Mariana Islands are the front arc. Similarly, Tonga Kermadec arc with Lau basin separating front and back arcs in Riku arc, it is seen that they are separated by Okinawa Trough of East China Sea. It is near Taiwan. Similarly, Izu-Bonin arc, the front arc is on the east and the Kisu-Palau in the western Pacific, south of Japan. So Izu-Bonin arc, Tonga-Kermadec arc, Mariana arc, these are all double island arcs. Besides these, we have Bransfield basin of the Antarctican country. It forms back-arc basin between South Shetland Islands, which are the fore-arc, and northern tip of Antarctica Peninsula, which forms the rear arc. The subduction of Phoenix plate beneath Antarctica plate produces these Shetland Islands, which form the fore-arc. Besides these, we have the Sea of Japan that forms the back-arc basin between Japanese arc, which is front arc on the east, and Honshu, Hokkaido. Japanese arc, the front arc is on east, which is Honshu, Hokkaido. With the Pacific and Philippines plate, Pacific plate and Philippine Sea plate subducting beneath the Eurasian plate, that is Amur plate plot plus Okhotsk plate blocks. They form the part of the Eurasian plate. So Japan Sea is the back arc basin. Japan itself is the front arc. Then behind the Japan Sea we have the back arc, represented by Korean Peninsula or Ryukyu or continental margin side of the continental arc. So Japan Sea, Japan itself is the front arc, and Korean Peninsula, Ryukyu continental margin side is the continental arc that forms the back arc. Similarly, in North Fiji basin, it forms the back arc basin between Vanuatu or New Hebrides arc, which is the fore arc, and West Santorini and other ridges which form the back arc. So these are the double island arcs. What happens here? Here Australian plate is subducting below the Pacific plate. That is North Fiji basin microplates along the New Hebrides trench. So the deepest trench found in Pacific Ocean is the Mariana Trench. It is followed by the Philippines Trench. So in ocean-ocean convergence, we have the features like trench, we have the Benioff zone, we have the volcanic arcs, fore arc and back arc separated by back arc basins. So double island arc is one of the most common features in ocean-ocean convergence, and in ocean-continent convergence the features that are found there that are also found here. And here in ocean-ocean convergence we find the volcanism to be of explosive nature, as we find all around the Pacific plate at its boundary region. We have the andesite line representing the circum-Pacific ring of fire. Now let us discuss how continent-continent convergence takes place. Here the two continental plates converge and collide with each other to produce fold mountains. We know that continental plates are very light. One cannot go below the other. So they collide and are forced to be raised up along their zone of collision. But in many cases, the continents are found to be part of the oceanic plates. As continental plates are less dense than oceanic plate, they cannot face subduction but face collision followed by upheaval to produce mountain chains. In such cases, what happens? One of the plate may initially be oceanic with continental plate on its one side. When faces convergence of the plates, the oceanic plate goes below the continental plate till the ocean plate gets completely subducted below the continental plate, so that the continental portion collides with the other continental plate to get deformed and to give rise to fold mountains, as it has happened in case of India. Indian plate was moving towards the Chinese plate, and in between them there was the Tethys Ocean. So Tethys Ocean was gradually closing because of the movement of the Indian plate towards the Chinese plate. So this ocean plate was going below the Chinese continental plate or Eurasian continental plate. So finally a stage is reached where the Tethys Sea was completely closed on the eastern side, so that Indian continental plate got the chance to collide with the Chinese plate to give rise to the Himalayan chain of mountains. So Tethys has been closed on the eastern side to form Himalayas, and the remnant of Tethys Sea is still there in form of Mediterranean Sea, and it is following the path of closing because African plate is moving towards the Eurasian plate and this Mediterranean Sea is gradually closing. So in case of this continental collision, the main feature that is produced is the fold mountain belts. So example is Indo-China convergence resulting in formation of Himalayan mountain chain. Besides these, we have several other examples such as Arab plate and Eurasian plate collision, collision of African plate with Eurasian plate to form Alps and Apennines. Similarly, in the long past, the Appalachian mountains of North America formed during formation of Pangaea. So these are some of the continent-continent collisions, examples of continent-continent collisions, and the major feature is the Himalayan evolution of the Himalayan mountain chains through collision of Indian plate with that of the Eurasian plate or China plate. Then what are the features that are very common to continent-continent convergence? Here we cannot say that there is the formation of a trench, no subduction of continents, as continents are of low density and they cannot go down. So here is the diagram that shows that this is the line boundary where Indian plate has been stitched with the Chinese plate, forming the suture. In the suture, here it has been stitched with the Chinese plate. There are two plates, two continental plates. One cannot go below the other, and they collide and they become stitched to one another to form a single plate. So here this is the suture zone, in the suture where this collision and stitching has taken place between India plate and China plate. As the continental plates are buoyant, they cannot subduct and both get united or sutured. And there occurs what happens because of collision, there will be crustal thickening because two plates will not subduct, rather they will face rise, there will be upheaval. Because of continent collision, the resulting crust gets thickened and upheaved vertically. It gives rise to high mountain ridges. Due to the above collision, high mountain ranges are produced with folding, thrusting and uplifting as main features of the rising mountains. Hence, these mountains are called fold mountains because Indian plate is moving towards the Chinese plate. So, the sediments here, they have been crumpled, they have been upheaved. So, we find the entire Himalayan mountain chain showing folding. So we have these raised hill masses, we have the plateaus, basins separating the hill masses. Hill masses is extending like this. So folding, thrusting, uplifting are the common features associated with continent-continent convergence, resulting in formation of fold mountains. Suture zone. The two continents, due to their collision, may get welded or stitched to form a single continent. The line of contact between the two plates may represent ophiolitic shoot of rocks produced through abduction, in which the fragment of oceanic crust which was carrying the continental plate towards subduction zone may be trapped with the other continental plate in the suture zone. So suture zones are noted for the occurrence of ophiolites. As we have discussed earlier, ophiolites are formed when abduction takes place between the continental plate and oceanic plate. So, in case of continent-continent convergence, one continent which was the part of the oceanic plate was carrying the ocean with it before collision. So, during the process of collision, the part of the subducting oceanic plate may be abducted, mixed with the continental masses to give rise to the ophiolitic shoot of rocks. So ophiolites are common features in the suture zones of continent-continent collision. And besides these, we have the shallow and deep focus earthquakes that are common to these continent-continent collision zones. As the continent collision presents the site of deep compression, stress, bending of rock layers, earthquakes occur ranging from shallow to deep focus. So shallow to deep focus earthquakes are common to convergent boundary zones, whether it is ocean-ocean convergence or continent-continent convergence or ocean-continent convergence. Here we do not find any volcanic arc. No volcanic arc is produced. But magmatism is found there, and these magmatic masses, they form the core of the fold mountains. And this magmatism takes place when the conjunction of the oceanic plate carrying the continent for continental collision was taking place. After closing of the ocean basin, no magmatism takes place. So because there is no subduction here, which is occurring in continent-continent collision to provide rock melt for extrusion and volcanism, therefore we cannot expect that the volcanic arcs are produced in continent-continent collision. So this is all about the convergent boundary zones of the lithospheric plates. Now we will discuss about the divergent boundaries that exist between the lithospheric plates. The divergence may take place in the oceanic plate, divergence may take place in the continental plate. So two types of divergent boundary can be expected, and let us discuss this. It is found along mid-oceanic ridges where two oceanic plates move away from each other. Where basaltic magma is found to be upwelled to form new oceanic crust or the mid-oceanic ridges. And as there is accumulation of lava to produce new crust, this boundary is called as the constructive boundary or these are called as sources. It is also found along the continents which face rifting due to operation of convection current and mantle plume beneath them, leading to stretching, thinning and rifting of the continents to form ocean, and finally at the mid of the ocean, the mid-oceanic ridge comes up to produce mid-oceanic ridges. And this cycle in which the continents are found to be dismembered, ocean comes in between the continents, again rifting continues, the extrusion of lava takes place to give rise to the oceanic ridges, and finally the new oceanic plate that is being created because of extrusion of lava between the two continents may become old, very old, dense, and it may face subduction, stretching or pulling the continents again together to form single landmass, and this process constitutes what we say the Wilson cycle. So continents rift, separate, develop ocean between them, develop MOR between them, become old, and finally become dense, undergo subsidence, and allow the continents to be pulled to collide with each other again to form single landmass. This process is called Wilson cycle. So, in case of divergent boundary, we have continental divergence and then oceanic divergence. Oceanic divergence causes the mid-oceanic ridges. So, here this is a figure where we find the mantle plume. It is the upper triple junction, and actually Arab was a part of Africa because of rifting and drifting. Here the East African rift has caused this as a microplate, this is another plate, and this is another plate. This is Arab, this is Africa, this is Somalia. These plates have been produced out of the African plate through mantle plumes, which causes rifting, lifting, and already the Arab plate has started moving in this direction from the African plate, producing between them this sea, which is called as a Red Sea. Red Sea is gradually developing, widening, and there is in the middle portion a ridge is gradually coming up, which will give rise to the mid-oceanic ridge in the Red Sea. And this Somali plate and this plate may widen further, and this may become a site for ocean in near future. So this indicates continental convergence, continental divergence, and because of which this Red Sea has been produced. This is the structure of the Red Sea, Gulf of Aden, and African rift system based on gas, IG gas. So the divergent boundary is found to exist between continents through continental rifting and at mid-oceanic ridges. So let us see what are the continental divergence, East Pacific Rift, that I have already discussed, Rio Grande Rift of USA, Dead Sea Rift of the Middle East between Jordan and Israel, the Red Sea Rift, Arab is moving away from African plate, producing Red Sea, which is gradually widening. So these are the examples of continental rifting. Then let us come to the oceanic rifting or oceanic divergence. Their mid-ocean ridges are produced. Almost all the oceans of the world present in their middle portions long narrow ridges which occupy about 1/3 of the surface area of the oceans. That results due to oceanic divergence. Example: East Pacific Ridge, Mid-Atlantic Ridge, Indian Ocean Ridge, Arctic Mid-Ocean Ridge, which is Gackel Ridge. The length of the mid-ocean ridges may range up to 65,000 kilometers with the width of about 1500 kilometers and height about 3 kilometers. So, mid-ocean ridges form prominent features in the oceans and they occupy 1/3 of the oceanic surface area. And almost all the major oceans of the earth present these mid-oceanic ridges. And they result due to divergence of two oceanic plates. Now let us discuss what are the features that are associated with the divergent boundary. So divergent boundary is noted for mid-oceanic ridges, rift valleys in the middle portion of the, if this is the plate which is going this side, this plate is going this side, in between the ridge will come up and the central portion of the ridge is found to present a valley, V-shaped valley, which indicates the site of oppelling of lava from beneath. And this portion is the boundary between the two plates. So here the rift valleys are found to develop in the mid-ocean ridges. The central portion of the mid-ocean ridges, the crests present rift valleys which are V-shaped, almost, or the contemplates rift due to operation of spreading mantle plume or convection current. As we see in East African rift, which has rifted due to mantle plume and hotspot at Afar Junction. And major feature of the oceanic divergence is volcanism. Mostly basaltic lava flows in non-explosive manner upwards through the divergent plate boundaries. The submarine volcanism produces pillow lavas on the sea floor. The volcanic rocks are found to be divided equally and drifted away from the ridge axis on two opposite directions along with the drifting plate, confirming the fact that the sea floor is expanding. It is further proved by paleomagnetic strips presented by the lava flows on both sides of the oceanic ridge. We have seen that if this is the ridge side, the plate move away, new mass is always created in the central portion of the ridge, the plates move away. So these are the ocean parts of the ocean. So ocean is found to enlarge through divergent motion of the oceanic plates. This is called ocean floor spreading, and this fact has been tested from the magnetic strips contained in the rocks which are produced from the lava. Always new rock is created at the ridge site and the plates are being pushed. So when the magma is undergoing cooling and consolidation, the magnetic minerals contained in them face crystallization and their alignment along the direction of Earth's magnetic field. So the magnetic minerals, they get aligned along the direction of Earth's magnetic field. So on both sides we have the magnetic minerals aligned, they are symmetrically placed, and they indicate the fact that the ocean floors are facing spreading because of this divergent motion of the oceanic plates away from the mid-oceanic ridge axis. Besides these, we have the hydrothermal vents associated with the mid-ocean ridges, which may be black smokers or white smokers that are found along the mid-ocean ridges. Mineral deposits of sulfides of copper, zinc, iron are found in these smokers, which are hydrothermal vents, because the magmatism takes place in the ocean floor. Water enters into the cracks, and reaction between the invading magma and the oceanic water takes place, and some of the economineal deposits in form of sulfides are found to be deposited along these vents, hydrothermal vents. Hydrotherm, thermally hot waters. So the magma is rising, water is going inside, so this will become hot and it will come up, and this will give rise to the vents, and there we find, because of this reaction between the percolating oceanic water and the invading magma, we find a congenial condition, and the reaction between the water and the invading rock types, which gives rise to, in certain conditions, is mineral deposits. So hydrothermal vents are common to the mid-ocean ridges. So the divergent boundaries are noted for volcanism, formation of V-shaped valleys, formation of magnetic strips on both sides of the ridge, then black smokers and white smokers associated with hydrothermal vents, which give rise to the mineral deposits around the vents. And in case of continental lifting, the ocean opens and lifting continues. In between them, the ridge develops, and finally a stage is reached when the continents rifted are brought back together to form the single landmass. As it has been seen throughout the geologic time that the continents have united to form single landmasses and have suffered rifting and drifting to form continents, and the last rifting and drifting has taken place over Pangaea, because of which we see the present distribution of the continents. Already sinking of some of the oceans have already started, and the cycle that starts from drifting, separation, and again the reunion through Wilson cycle takes place around a time frame of around 500 million years. So the present continents which have been produced by rifting will face convergence and unification in times to come. Besides these, we have some other features that are associated with the mid-oceanic ridges. These are the transform faults or transcurrent faults and fracture zones. When the ocean plate is separating along the mid-oceanic ridge, the rate of motion of the plate is not found to be uniform on both sides. Again, the rate of extrusion of lava is not found to be uniform. So, the plates which are drifting, they face tension. So, these are found to be cracked. These are found to be cracked. In this manner, the mid-ocean ridges are found to be drifted. So, they form here, they form the transform faults, these transform faults. And the transform faults may be converted into transcurrent faults. So here we see this is the, because this ridge was like this. Now they have been dismembered and placed here. So here this is the transform fault. So transform faults are very common to the mid-oceanic ridges. In case of transform fault, we have this portion. This portion is fixed; it is not changing. But in some cases, this length of the transform fault is found to change. This plate moves in this direction. This plate moves in this direction, and this is found to lengthen. Here we say it has produced transcurrent fault. So transform fault and transcurrent faults are common to the mid-oceanic ridges. It results due to unequal movement of the lithospheric plates. It results due to tension, and as a result of which fracture zones are created. Transform faults and transcurrent faults are created. So divergent motion of the oceanic plate from MOR is not found to be uniform over the entire plates, and again oppolling of the lava may not be uniform at the divergent boundary that pushes the plates outward. Thus, the MOR is found to be traversed by strike slip faults or transform faults or transcurrent faults or fractures, as a result of which the ridge gets dismembered, drifted in different rates in order to be consumed finally at the convergent boundary zones. So this is the ultimate fate of the mid-oceanic ridges. And beside that, we have the shallow focus earthquakes are common to the mid-oceanic ridges. As basaltic lava flows are fluid-like, the erosion takes place without violence, and therefore earthquakes resulting from magma extrusion cannot cause major earthquakes. Again, the crystal portions of the MORs are affected by block faulting or normal faulting, like this. Normal faulting. This forms the V-shaped valleys. So normal faults at the crest portion of the MORs. So there we can expect shallow earthquakes, shallow focus earthquakes at the crystal portion of the diverging plates at the mid-ocean ridges, and these shallow earthquakes are common there compared to the deep focus earthquakes which are found in convergent boundary zones. And in case of continental rifting, we find the formation of new ocean basins. Here at early stages of divergence, there causes development of rift valleys with further widening of the rift valleys because of convection currents spreading. The rifts may link to oceans and seawater enters into the rift to form new oceans. Example, Red Sea in African rift system. Subsequently, the sea widens and becomes a site of formation of mid-ocean ridges, as it has happened in all the mid-ocean ridges. So, these are the different features that are found to be associated with divergent boundaries. So, we discussed that divergent boundaries are noted for shallow focus earthquakes. They are the sites where new ocean is created, particularly in ocean continental divergence. The transparent faults and fracture zones are created at MORs. Hydrothermal vents are associated with the mid-ocean ridges where mineral deposits are found to be associated. Volcanism, formation of rift valleys, formation of V-shaped valleys are common to the mid-ocean ridges. So these are some of the major features that are found to be associated with the oceanic divergence and continental divergence. Now, we will discuss about the third type of boundary, which is transform fault boundary or conservative boundary, where there is neither creation of any new landmass nor destruction of any existing plates takes place. So that's why they are called conservative boundaries. These transform fault boundaries are called conservative boundaries. These type of boundaries seen in oceanic ridges linking ridge to ridge or ridge to trench or trench to trench. Also it is found within the continental plates. It may be found in the oceanic ridges, it may be found in the continental plates. Example of continental rifting is San Andreas Fault of California, linking Juan de Fuca Plate to the East Pacific Rise. So this is the MR, this is the ridge, Juan de Fuca Ridge, that was forming the part of the oceanic Pacific rise in the past, but now it has merged with North American plate in ocean continent convergence. So this Juan de Fuca ridge is linked with East Pacific rise by this transform fault, which is called as San Andreas Fault. And beside this, we have some other faults in the continent, such as Alpine Fault of New Zealand, joining Pacific Plate on east and Indo-Australian Plate on the west. Similarly, North Anatolian Fault of Turkey, which joins small continental block carrying most of the Turkey, that is Anatolian Plate, with Eurasian Plate on the north. Besides this, we have the Philippines Fault, we have the Atacama Fault of Chile. These are some of the continental faults and oceanic faults. Along this boundary, transform fault boundary, there is neither creation nor destruction of plate material, for which this boundary is called as conservative boundary. These boundaries are essentially made up of strike slip faults, where movement of plates takes place parallel to the fault plane. These are called transform faults because the type of motion between the plates changes or gets transformed at the end of the active part of the fault. For example, the divergent motion between the plates at the mid-ocean ridges can be transformed along the fault to the converging motion between the plates at the subduction zone. That's why these strike slip faults are called transform faults that connect convergent to divergent plate boundaries in various combination. So here it is linking the mid-ocean ridges. This is the transform fault. Here transform fault is linking to the trench and the ridge. Here this plate is heavy, this plate is light. That's why it is arc shaped with convex side to this side. Here arc is convex towards this side. Here two arcs separated by the transform fault. So this transform fault links ridge, trench, and we should always remember that the convex side always faces to the plate that undergoes subduction. The convex side always faces the plate that undergoes subduction. This we have to remember. So divergence. So these transform faults connect the ridges or trenches in these 6 types of combination. So we have, so this is the diagram, this is the Juan de Fuca ridge, the San Andreas fault, links to the Pacific ridge here. Here it is Pacific ridge. This is the transform fault or the San Andreas fault that links the Juan de Fuca ridge. It is having its location within the continent, California. So it is a transform fault associated with the continent. Most of the transform faults are located in the mid-oceanic ridges. And we have the transform faults in the oceans, such as here these portions. This is Pacific plate, new hybrids, and these are the Tonga Kermadec trench areas. There we see this type of transform faults. Here the transform faults near Scotia. Here the transform faults linking the, separating the Eurasian plate from that of the African plate. So these are the sites where we have this, that is continental. Here it is the Californian occurrence, continental, San Andreas fault. Oceanic occurrence, linking the ridge. This is the mid-Atlantic ridge joining this. So these are the places where we find the transform faults. So this is all about the transform fault boundaries. So we discussed that transform faults, fault type of boundaries occur within the continent and they occur also within the oceans. These are essentially strike slip faults, and because they may be joining the divergent boundary with convergent boundary, or the plates are found to be transformed from divergent plate to convergent plates. That's why these strike slip faults are called as transform faults. And we have neither creation of any land, not destruction of the land along this plate boundary. That's why this boundary is noted as the conservative boundary. And these boundaries are not associated with deep focus earth. They are associated with some of the major earthquakes, because they occur sliding past of one plate with the other, and they are associated with major earthquakes. For example, the San Andreas fault, that is associated with a very devastating earthquakes. For example, the last earthquake which took place, which was of devastating nature, that took place in 1906, and at regular intervals along this San Andreas fault the earthquakes occur. So the transform fault areas are noted for earthquakes. So this is all about these plate boundaries, and now we'll switch over to the next item, that is the motion of the plates.